Hello, our next speaker is Howard Penrose, who is the president at MotorDoc LLC, and will be discussing detection of bearing and lubrication defects in wind turbine powertrain with electrical signature analysis. You can find out more about him and connect in the speaker profiles.
Hello and good afternoon. I hope everybody's doing well. I'm hoping to have a little time for questions at the end. And if there'll be some animation in here, if I shut off my video, I'm not that interesting, everything else. That is so that we can, school's back in session in this area, that has an impact on my ability to stream. So today we're going to talk about electrical signature analysis. It's something that most are kind of aware that I'm doing, but really we're doing full system analysis of wind turbines with electrical signature analysis. And I'm going to get in a little bit into that because the concept that people have read since sometime in the 1990s was electrical signature analysis was for the detection, or current signature analysis as well, was for the detection of rotor issues, and that's actually not correct. The original concepts, see if we can get this going here. The original concepts had to do with let's try this again. There we go. The original concepts had a much broader meaning. So within the United States, as of yesterday, there were 67,762 wind turbines operating all over 1.5 megawatt. So that's those are the common machines, right around 1.5 to 2.5 megawatt onshore. Offshore, they're much larger. In the U.S., in order, Texas is number 1, Iowa is number 2, Oklahoma is number 3, California falls down into number 4, surprisingly, and our moderator, just so you're aware, Kansas is number 5 or 6. 5. Illinois, where I am, is number 6. So there are, as you can see from this map, a lot of wind kind of in the center of the U.S. and down through Texas. It just happens to be where the wind maps show the best locations. We'll talk about wind turbines real quick so you understand what they are and what they look like. This is a wind turbine. This was up in Minnesota, actually, and a wind farm, whenever you hear that term, is a minimum of 10 towers. Usually it's 20 or more. The full utility scale ones will be as many as 100 to 200 towers on a single farm. They are tall, meaning the average height of a turbine will be about 315 feet. So if I say S88, that actually means the hub height is 88 meters off the ground, and the blade diameter tends to be the same as the height of the machine. Some of the newer turbines, the blades are a little bit longer. So when you hear that number at the end, it usually refers to that hub height in meters. This one picture in the middle, just to put it into perspective, that little dot in that blue circle, that's a person who's rappelled down that blade. This is a Siemens Towers, rappelled down that blade to do some repairs. So they are of a good size. Internally, and hopefully this video comes out well, this is a nice visual. The bottom part here, this is how it rotates. There's usually 3 or 4 of these yaw motors. Those are easily replaced, so they don't focus on that as much. This generator in back, they do focus on. Replacing a generator is $150,000 to $250,000 to get it up and down and replace. A coupling, a gearbox, that's $500,000 to remove and install one shaft. Then you have your blades and the hub. in which they have pitch motors to turn the blades, and that's how they control the speed. Now, these will turn between 14 and 20 RPM, depending on the size and diameter of the blade. You have all of these systems in here that you have to maintain. There's a lot of bearings. There's 2 main bearings. You have all the bearings in 3 stages and a planetary gear set in the gearbox and everything else. Another thing you have to consider is that they're not running full power all the time. As a matter of fact, the average in the US is they're running at about 35% load. So there's certain conditions that are happening during this power curve down here between about 3.2 meters, which is about 7 miles per hour, up to about 10 meters per second for those towers. There are newer towers that will be able to start right about 3 meters, and some older towers that require 4 meters per second, or about 10 miles per hour. You, of course, have wind gusts, which affect what goes on. What you see down here in the lower right, this is a snapshot from electrical signature analysis of a tower that's starting up. So this impulse here is the initial start, then it goes into a soft start, and then it's relatively low wind at 5.8 meters per second, which would be down here, with some gusts as it coming up to speed across 240 seconds. A lot of things going on in there. That's as part of a study we're doing on the reliability of these machines overall. So we take a look at the types of failures. Bearings, of course, are number 1. Why not? They are ball bearings in virtually every land-based tower that exists. So, and we're not talking about small ones. So the bearings in the generators will start at, say, 6228 on up, and they will be ball bearings. And the larger the bearing, the slower the machine. So a lot of them run between 1800 and 1200 RPM. The rest of it is stuff that's going on inside the turbine in this case. When I start talking about a complete wind turbine, the generator is number 3. Blades are number 1 for failure. Generator is number 3. Gearbox is number 2. The main bearings do wear out, and they're number 4. Kind of put it in perspective, this is a generator. This is a 2.5 to 3 megawatt, depending on what tower it goes into. This is unusual. There's only a couple of them out there that are 12 kV and 6 kV. A majority of them are 480, 575, and 690 volt. They all put out 60 hertz. Most of them are a wound rotor type tower, wound rotor type generator, I should say, that's referred to as either a singly fed induction generator or a doubly fed induction generator. The doubly feds have a variable frequency drive that feeds the rotor, and all of your actual 60 hertz comes directly off the generator straight into the grid. So only with less than 10% of the towers in existence will actually have an inverter between the generator and the grid itself. So a lot of control going on up here, and they impact the bearings. Here you can see virtually every tower or every generator will end up having a shaft brush, and will usually have an insulated bearing or set of bearings in there. This is a running generator being tested. This is what it looked like when it had failed. So one of the most common failures for the rotor is a catastrophic failure of the connections. So a lot of reasons behind that outside the scope of the presentation. And then, of course, wedges, primarily having to do with changes in the conditions of towers. So they'll freeze and cool, freeze and cool, freeze and cool, freeze and cool, especially during certain times of year, or heat and cool, heat and cool, heat and cool, depending on the application. This dark blue means that this is actually a northern climb turbine for this manufacturer, and that thermal cycling actually causes all the plastic inside the machine to crumble. We would pick these up and just kind of crumble them in our hands. These were designed to go down to minus 40 degrees centigrade, but the application for this particular turbine was as low as 55 below. So as you can understand, that also means we have to pay attention to what's going on with the lubrication. The gearbox and the main bearing. So this is a common gearbox up here on the left. This is how it's usually configured. High speed, which is the generator side. Low speed is the input. So it's kind of in reverse. So I have my low speed coming in, that 14 to 20 RPM, to a planetary gear set, and then it steps up. The lubrication for the generator is, for the gearbox is very important, as it is for this guy down here, which is the main bearing. This is one of two that would go in this system. So they're large, usually double roller bearings. And the primary thing we see here is they're usually flushed out periodically, once a year, once every other year, depending on which maintenance practice the site is doing. They have to go in and clean out the dry grease in the bottom. If they don't, you see it. It actually, the rollers will ride up and over that. And we will see that in electrical signature analysis somewhere between 4 and 6 hertz. So when we see that, that indicates that they did not properly clean the bearing. Now, the nice thing about doing a site that has between 20 and, say, 200 towers is you learn very quickly how well the site is maintaining different components, especially in the main bearings. To put it in perspective as well, here's what the inside of a larger tower looks like. This is the control. And we've had cases where, we can fit a dozen people in the base there. But this ladder is how you get up. And that, by the way, in the upper right, that is the first layer. So if you have to climb, you go up, you stop there, you go up the next one, you stop there, you go up the next one, you stop there, and then you go to the nacelle. And they are vertical ladders. Some will have elevators in them, but they're not the type of elevator you go to in a commercial building. This guy down here in the lower right, that is an older style G.5 tower. You can fit a few people in here, but it's pretty tight. So let's get to electrical signature analysis, which was developed at Oak Ridge National Labs in the 1980s. The same technology is used, but you need a very high resolution in order to take a look at the different peaks that we're considering for different types of failures. So this one here, just to give you an idea, this is not normal. This tower up in the upper left, we were able to get it to run for 5 minutes so we could collect data. This is very atypical of what we'll run into. The one down here and below is more typical of the types of signatures we have to look at. In this case, I have, that would be main bearing. This would be running speed. No, that's a planetary gear set. And then out here would be the running speed. Usually I have to look in voltage or current, depending on the speed and load on the machine, or both. And that's part of the secret behind doing electrical signature analysis on a tower. You have to know the actual condition it's running in order to know what you're analyzing. So there are a number of things that we're studying on towers with electrical signature analysis, but the key was the ability to take a look at gearboxes. So gearboxes in wind turbines are designed to not have what you see on the right. So if you see oil leaking out of a tower on the external portion of the tower, that means there's a skirt up there that is not functioning properly. You can tell when the gearbox has blown a seal or a hose when you walk into the tower, because you will step into a pool or a lake of oil. It's not been unusual to walk into a tower to collect data to literally have it raining oil. When we go in there, the first thing we look at is what the conditions are up tower, so we know whether or not that oil leak has actually done damage to the gearbox. So if I see it on the external side, that is bad. If you ever see it, get a hold of the wind company in that area. There's usually going to be some kind of sign up with a number. Contact them. That is bad. That is an environmental issue. But when I'm taking a look at a tower such as that exact one, we need to take a look at bearings, etc. And the last presentation, I'm going to show you how that's calculated. The good news is you can see here, inner race, outer race, cage, and ball spin. Those are the exact same multipliers we use for vibration analysis. So in electrical signature analysis, we calculate it exact same way as you would in vibration. And I usually tell people jokingly, if they're in the vibration end of the business, how you look at electrical signature analysis is stand on your head and cross your eyes. So I'm looking for values from my peak in voltage or current down to some value. So in this case, those would be my multipliers. And then in this case, we're taking a look and we're seeing some issues in my high-speed main bearing and the mid-speed opposite drive end. That's unusual to get them in the middle. That if I see them in the middle, it usually indicates there's some kind of oil leak or the oil pump is not operating properly. So when I start taking a look at it, again, the peaks occur, so it's my line frequency. I can look one direction or the other. I usually look from the line frequency to the right, and I look to see if those peaks are there. If I see a peak there, I look to see if there's a mirrored peak to the left. This one's running at a low load, so I'll primarily look in current. It's a doubly fed induction generator, so it actually kind of acts like a load. The rotor becomes a load, so I will do current signature. If I'm at the higher end of the power spectrum, I actually drop down and I look at voltage because now it's a pure generator. But I'll take a look at those peaks, see what's there, and there's a very definite set of peaks. And whoop, I thought I had the picture of that gearbox, but I do not. We took the gearbox out and we had planetary gear issue as well, and that was pretty bad. The main bearing, here's an example of a main bearing. That set of peaks on either side. If I have a large number of peaks around either side. Now, I've heard people use a rule. The peak on the left or the peak on the right. That actually has to do with the type of filter you're using in the system. So if I'm using a Hanning window or I'm using, I use a flat top window when I'm doing my analysis, that decides kind of where my signature is. So I'll look at either side. If I have a lot of noise around one of my peaks, that means there's some chatter going on. This is usually an indicator if I don't have anything other than an outer race signature with that bearing. That would indicate that dried grease is in the bottom. The correction for that is actually done up tower. It's inexpensive. They go up a little alcohol, get that old grease out, and re-grease the bearing, and they're off and running. That's it. So let's take a look at a tower. So this would be a GE 690 volt, 1.6 megawatts. So it's slightly larger with a Hitachi generator. 6-pole, and they've got 6330M bearings on both the drive end and opposite drive end. So kind of a tower like this. And for those who are into environmental jokes, this is carbon neutral because I have cattle and then I have wind. So, I start taking a look in here. Now the signature I'm looking at here is a little unusual. I don't like to see it. That one up here on the upper left. Those extra peaks there, those are actually frequencies associated with gear meshing in the planetary gear set. So that means that they have an unbalanced planetary gear going around on the ring. That will eventually cause a failure. The two little peaks in there are conditions I'm looking for to see if there's something going on with the rotor. That's part of several things. This one had just been worked on. So this could be alignment of the main shaft to the carrier. None of the wind companies, none of the OEMs do any such alignment of those. As a matter of fact, there's some that believe in not doing the alignment between the gearbox and generator. That's a whole other topic. So there are a few issues with this tower. The work was just done. There was a spacing issue in the tower on the coupling. So they started seeing on a brand newly installed bearing, they saw some small minor peaks. It was under load, under a heavier load, so those peaks show up in voltage. So I'll take a look and see what those peaks look like. So it's a ball. The ball frequency is going to be at 107.8 hertz, the outer race at about 132.4 hertz, and the inner race about 169.2 hertz. If I don't know the exact manufacturer, I'll pick like SKF or NTN. Those tend to be pretty common, and that'll get me in the ballpark. I might be off by a fraction of a hertz, but it'll get me right there. So I'll take a look at that. And then the other thing I can do with full electrical signature analysis is look at my power or my kilowatts. So if I want to see the impact of friction in that area, I can take a look at this. And so the ball here is a small peak, and it's kind of lost in the noise, but it's valid. So I'll take that. That's about 1 kilowatt. Outer race, also about 1 kilowatt. Inner race, about 0.4 kilowatts. Now, one of the important things when I'm doing kilowatt analysis is all my readings are 1 time the value, not peak pairs. That again is another slightly different topic. The thrust bearing in the gearbox is what tells me that I'm having a bit of a problem with my spacing and the coupling. That is at about 8.6 kilowatts for a total of about 11 kilowatts under those conditions. So went ahead and replaced the bearing. The bearing was shipped up to our lab. We took a look at it, and there's some false sprinelling on the inner race, some false sprinelling on the outer race. As you can see, this is a ceramic coated bearing, so that's an insulated bearing. And on the far right, you can see that's a ball that dragged, and most of them are good. But this particular one got caught and dragged. Unfortunately, somebody had cut the cage out, so I didn't get a chance to see if there was also cage damage. But we had basically a skidding ball, and it was right at the point where it would have started flaking. So we went ahead and took readings immediately after the bearing was replaced. And as you can see here, those peaks that we showed, they were relatively low in the first one. They're pretty much gone. And my peaks are now much lower. I will always have some level of peak associated with the bearings. You always have some level of friction, but we dropped it from 11 kilowatts to about 2.43. And the big one here is the thrust bearing peak is pretty much gone. I still have that planetary gear set issue. That's a whole other thing to look at. But here on the lower right, the peaks associated with the inner, outer race and ball are gone. Now, what's important on this one here and on the previous one for kilowatts is that was done at the same wind speed and same loading within a few kilowatts on the tower. And it's hard to control that, but we were able to, in order to validate that we had gotten there. So I'm going to have to turn this off so that I can see if there's any questions. And we have lots of time for questions. I spoke really fast this time. By the way, if you're wondering, this tower here in the picture or in the video is up in Saskatchewan. That was a lot of fun too. But let's go ahead and we went off. Oh, and that background there, that was my trip last month. That was in Idaho. So these turbines are everywhere. Let's go ahead and stop sharing that. And I will turn my picture back on.
Hello.
And let's see if we have a question or two.
We do not. Does anyone have a question for Howard? Anybody? Someone did say, good to participate in your presentation. You were full of knowledge. That's nice.
I appreciate that.
Someone said he has a question.
Okay.
I'll wait for him to type.
Yep. Yeah, actually, we were up testing wind turbines yesterday. So it was up in northern Michigan. It was a lot of fun. The summer is a bad time to do it.
Is it hot?
There's no wind in the summer.
Well, we're waiting. Are you using a software package for this or on a programming language? e.g. MATLAB?
So this is my opportunity to talk about the product I use. It's actually the Empath electrical signature analyzer. In order to get the type of data we need to separate everything out, I have to take over 12,000 samples per second and then be able to process that. The system that we use was developed for nuclear power by Oak Ridge National Labs back in 1983 and patented in 1989. So that's what we use. That system allows us to go into the base of a tower and do analysis. Does a generator fault, even if minor, mask gearbox noise? Not in electrical signature analysis. Yes, in vibration, and that is one of the issues and one of the reasons why we're looking at it. Now, there's a difference between vibration and electrical signature analysis. Electrical signature analysis looks at the entire system at once. It uses the generator, or I should say the magnetic field between the stator and the rotor. That's the transducer. So so I'm taking a look at everything both directions. Now, what does happen is I will see mechanical conditions such as bearings at a later stage. But I do get to see them all at once, which means that when we do detect a bearing, we're either doing a visual inspection or the service company is doing a visual inspection, or we'll double it up with vibration to see how severe it is before actually taking action, because it's quite expensive to take a tower out of service for, at least if we're doing it up tower, a couple of days. Let's see.
Someone said,
there any... I'm sorry, go ahead.
You mentioned windowing. Is there averaging done or not?
Oh, yeah. Yeah, I'm actually just taking 3 averages. But I could take 3, 6, or 9 averages. I just use 3. And the nice thing is that when I take more than that, I mask certain things, including what's called subsynchronous resonances that occur that are causing other conditions in the tower. So we're trying to look at both electrical and mechanical conditions, and we're seeing the entire powertrain at the same time.
Someone said,
oh, go ahead. Sorry.
Is there any difference in detection when using black oxide bearings?
I don't care what the bearings are, really. We just look for the signature. But no, there's no difference in the bearings. As long as we have the frequency, if there is wear or damage, we'll see it. And they're not 3.
They had a typo.
Yes, there is everything done. Yes, it's 3. It just happens to be the same.
Yeah. Any more questions?
This is a hobby, not just a job. So if anybody has questions later, please feel free to ask. Right now, we are the only ones performing this type of work, doing this type of work. But we have service companies, and the sites are also doing this type of thing in the field. Do I see fluid film bearings? Fluid film bearings are seen primarily as a static eccentricity or dynamic eccentricity, depending on the type of fault, along with certain other conditions. Yes, electrical signature analysis, you have to do both voltage and current, all 3 phases, for a generator of this type. It is a supersynchronous type generator or asynchronous generator, meaning that it's running greater than, say, if it's a 1200 RPM, it could be running as fast as 1400 RPM. What's important in a wind turbine, and I'm going to give away a little secret, is that the way the wind turbine acts so that it puts 60 hertz out is it has a counter-rotating magnetic field in the rotor that brings all my frequencies back to 60 hertz. So I have to know what the rotating frequency is in the air gap in order to determine what all my other frequencies are, because those are all brought back down to what it would be if it was saying it running at 1208 RPM. Which is one of the more common speeds, even if it's running at 1400. It's a hard thing to get your mind around, but it really works that way. So when I go in, they say, well, do we need to take a tach reading on the wind turbine? I said, only if you want to miss everything. So,
We have time for just one last question.
Yep. Skylar, absolutely happy to respond and give you some ideas, regardless of whose technology you're using. And then do wind turbine gearboxes need high pure quality of oil? Yes, especially if you want them to last. They're in a really rough environment. I don't know. The part I'm involved in the powertrain committees at AWEA and ACP, in the introduction, I just within the last couple of weeks became the vice chair of the technical standards committee. I'm focused on the electrical side. I am aware of what's going on with the lubrication because I was part of the committee that put together the gearbox standards for wind turbines, but I was more focused on the analytics and less on the oil. But if you reach out to me, I'll be happy to get that information for you anytime.
All right, that's all the time we have. Thank you, Howard, and thank you for
everyone
participating. And see you
thanks
later.
for being a great moderator.
Thank you. Have a nice day.
Okay, thank you very much.
Bye-bye.